Hello and welcome to the second episode of the Operating System Development Lecture Series. First of all, I would like to highly apologize for the unchanging video resolution. As of right now, I am having some problems related to my hardware, and I sadly cannot physically change the resolution, but it will get better in February. I've already tried messing with some other video settings, so I hope it looks a little bit better than in the previous video, but I apologize for the fact that the resolution has not changed. Yeah, so let's get to the actual lecture topic, which is going to be booting. So right, we have an OS, which is a bunch of code, right? And we want to somehow boot it on our machine, right? So when you write a program, usually you already have a user space of your operating system that actually allows you to execute this freely, and it's a very simple process. But how can you actually force your machine to do something like that? Well, for that we have to take a look at what happens when you press the power button on your computer. And the first non-trivial thing that happens is launching the BIOS, or the basic input output system. So if it comes to the BIOS, it is good to talk a bit about its history, to sort of fully understand our current standpoint if it comes to booting. So BIOS used to be a very general name. I mean, every computer, or at least like every computer from a different manufacturer, had a different BIOS, or a different computer model would have a different BIOS, right? And they would be drastically different, right? They would have a completely different way of operating, but they would still all be the BIOS, the basic input-output system, which was, well, responsible for booting and for, as the name suggests, performing basic input-output operations. So it wasn't really standardized, but then there was an actual standard that arose, and it was the IBM PC BIOS. So the IBM PC BIOS became sort of standard that, well, the way we know it today, it appeared in it appeared around 1981, the way we know it today, and it was simply a very common standard, and a lot of manufacturers started to, well, at first it was just IBM compatibles, right? But then pretty much everybody wanted a motherboard with something resembling the IBM PC BIOS. And it was used for a very long time, but then around 2002, there were some theoretical thoughts of something that actually could be better and way more sophisticated. And this was supposed to be UEFI, or Unified Extensible Firmware Interface. And basically, if it comes to UEFI, it was, the first theoretical stuff was in 2002. In 2004, they started to release the first official versions, but UEFI, again, as we know it today, appeared in 2006. This was the release of 2.0's version, which really set a lot of the important values in a UEFI BIOS. And the previous versions, they had a lot of bizarre stuff that isn't really associated with the UEFI BIOS anymore. But it obviously wasn't a drastic transition. It wasn't the fact that, okay, we've been using the IBM PC BIOS standard for like 2 decades, and we're going to now change all of our computers to the UEFI. No, it wasn't like that. In fact, for manufacturers to actually start caring about putting UEFI in their motherboard, it took like 2-3 years. It was in like 2008, 2009. And even then, a lot of people still resorted to legacy booting, and many OSs still did not support UEFI or had very minimal support for UEFI. It was only with the release of Windows 8 in 2012 where people actually started using the UEFI as it became the recommended thing to do. So after like 3 decades of using the IBM BIOS mostly, people have started to use the UEFI in the later 2010s. UEFI became the most popular booting method, and this is probably what you're using right now. In fact, some manufacturers even decide not to even include this IBM PC BIOS standard in their motherboards anymore. But this is not that common, and it's mainly, I think, in laptops. So this was renamed to the Legacy BIOS. And another functioning name is CSM, or Compatibility Support Mode. And this is how you'll see the Legacy BIOS being presented on a lot of modern motherboards. One thing I would like to point out is that the Legacy BIOS isn't dead, as in there are still a lot of people who voluntarily use the Legacy BIOS. I do. I'm currently running all of this. I booted this off of a Legacy BIOS, despite my motherboard actually supporting UEFI. A lot of people using like older hardware, but not only that, they choose to use the Legacy BIOS. But even though I don't think it's dead yet, I think it's slowly coming to an end. I think it won't last more than like 2 decades, and UEFI will really become the new standard, or perhaps there will be something completely different on the rise. We don't really know that. But I'd just like to make a remark about the nomenclature of these. Because what is interesting is that another functioning name for the Legacy BIOS is simply the BIOS. So this might seem a little bit strange, so let me clarify. Back in the day, in like the 70s and stuff, when computers started to have BIOSes and they would all have a different BIOS, BIOS was a very general name. But the moment the IBM PC BIOS became the standard, right? The moment it became the standard, people started to associate BIOS with the IBM PC BIOS. It pretty much became the same thing. So whenever someone said BIOS, they really meant this standard, right? And because of this very strong association, when UEFI released, people didn't really call it a BIOS, right? So in many communities, if you say BIOS, right, still they will think that you're referring to this. They'll know that you're referring to this. So it's this whole thing, and, you know, some people say like BIOS versus UEFI. And I'm not saying they're wrong, because yes, it's a properly defined nomenclature. But it's personally not something I like to use. There are many arguments for saying that, for why you shouldn't say that UEFI is a BIOS. Like, for example, the basic part, right? It's not really a basic input-output system. It's a big firmware. Well, sure, but many BIOSes were considered big at the time, and all of them were still called basic input-output systems. And, well, what is a UEFI fundamentally? Well, it does primarily boot services, which are just like input-output stuff, and they're still relatively basic. So I mean, it's still a BIOS in a sense, in the sense that you can say it's a full-fledged input-output system. So I personally prefer to say that this is the legacy BIOS and this is the UEFI BIOS, or just UEFI. Rather than saying that this is the BIOS, this is the UEFI, but both nomenclatures are correct depending on like which people you're talking to. So this is an important thing to notice. But it's just nomenclature, right? So I would like to talk a bit about why I chose to primarily present the legacy BIOS in this series. And it's highly related to how many older stuff actually functioned. So if some of you had the Commodore 64, you might know that this little joystick entry that it had, the joystick port, was extremely simple, right? It had 9 pins. One of them was a voltage out, and all the other ones were simply corresponded to some function of the joystick, like up, down, left, right, A, B, right? It was an extremely simple system, and everything you had to do to build a joystick, and in fact, I sort of did that. Not like a full-fledged one, but just, again, just some buttons on a breadboard. Everything you have to do in order to build a proper quote-unquote joystick is to ground those pins. It's that simple, right? You have to ground those pins. You simply ground a pin and it corresponds to its functionality. Another, like, let's say, older interface, VGA, right? The VGA cable has 15 pins, right? And it was very easy to communicate different image data with that. That is because every pin has some very simple function. Many of those pins are actually optional. And you would have like a voltage drain, and you would have like a red pin, a green pin, a blue pin, and you know, there would be like a voltage, what do you call it? You would have a minimal and maximum voltage, and they would correspond to, you know, how much of red do you want, how much of green do you want, etc. It was a very simple interface. Now take a look at what happened now. So now we have more sophisticated interfaces. Now, this isn't necessarily a bad thing. I would just like to point that out. I mean, we need for our technology to become more sophisticated, but there's a certain pretty sad consequence of making technology more sophisticated. Basically, think about like a modern joystick. You don't have a joystick port on a modern computer. You have something like a USB port, right? The universal serial bus. And basically, it is not so simple to make a USB joystick. You know, making a USB device is not so simple, just like on a breadboard. Well, making a joystick back then, very simple, just ground the pins and it corresponds to the functionality. USB is a very sophisticated interface. I'm not saying that's a bad thing, but what I'm saying is that there is the sad consequence of you not being able to build stuff with it anymore. VGA, right? VGA was very simple. You could plug some things into a breadboard. You would send voltages to some pins, and that would be it, right? Now think about a modern video interface like HDMI, right? Well, it's way more difficult to deal with. You can't just build a simple video card like you would do with VGA. HDMI is a way more complicated interface. Now, why am I saying all of this? That's because I want to really justify my use of the legacy BIOS in comparison to the UEFI. Yes, UEFI is newer. It has some very cool stuff for the actual user of UEFI. But the thing is, it's way more sophisticated in the sense that you can't play around with it just like you would play with older stuff, like the legacy BIOS. The thing about legacy BIOS is when people make bootable code for a legacy BIOS, they usually do it all by themselves because it's very simple and you get to really understand what's going on. The thing with UEFI is a lot of UEFI OSDevs, and again, I'm not saying whether that is good or bad, don't actually fully understand UEFI. They use some external library and they use external tools in order to get something booting with UEFI. And this is sort of against this philosophy I was going for, because I wanted to choose an interface that I can really show how you can like tinker with it. And the thing is, I'm not saying it's entirely impossible with the UEFI. I mean, it obviously is, but it would probably prolong all of my initial videos by like a minimum of 2 hours. And on top of that, I'm not that experienced of a UEFI developer. Yes, I have gotten stuff booting, I have used boot services, I have gotten some basic OS functionality on that, but I still don't feel like I understand every aspect of it. So for those two main reasons, I decided to go with the legacy BIOS. I am going to talk about the UEFI BIOS in this lecture, but it's not going to be in such an amount of detail as with the legacy BIOS. Yeah, and that is pretty much everything I wanted to say, I think. So now that we know what a BIOS is, let's talk about what the BIOS actually does when you boot your computer. So the first thing that the BIOS does is something called the post. This stands for power on self-test. So this is basically a test that the BIOS does in order to determine, hey, is everything fine with me? And all the other hardware on the motherboard. Now, if everything is indeed okay, then it will continue to the next step, which I will talk about. But if something is wrong, then it means that something failed, power on self-test, and it will usually display an error message. This message being pretty key for example, someone who wants to service this computer that doesn't boot, right? So it can be an error message. Some OSs don't have an error message. It depends. So you have a power on self-test. Now, if the BIOS passes, well, if all the hardware passes the power on self-test done by the BIOS, then the BIOS goes to its boot priority list. This is a list of different mass storage devices that can store an operating system. So You can see this in your BIOS configuration. It's very easy to enter your BIOS configuration usually. It's usually a key which is a shortcut, and you simply have to press the key while booting up your computer. This is usually one of the function keys. So you simply boot your computer. If you're not scared about breaking your keyboard, you mash all the function keys and you'll probably get in your BIOS configuration. And somewhere there you will see the boot priority list, which will have a bunch of mass storage devices. So for example, you probably have your main operating system on some hard drive, so it might have a hard drive there. But you might have another OS that you often use, and you might, for example, boot it off of a USB stick. So the second thing might be a USB mass storage device. And then, you know, it might have some other boot option, which is not really that common for you. For example, it might try to boot from the network or something. So this is the boot priority list that it has. But there is a certain problem with that, right? So let's say that you changed your priority list to have the USB mass storage as having maximum priority. And then let's say that you have a USB stick with, let's say, your childhood photos, right? Just generally any data that you could have on a USB stick. So let's say you plug in the USB stick with your childhood photos into your computer, and then you try to boot it. So the first thing that the BIOS is going to do, right, if your USB mass storage has maximum priority, it is going to try to boot off of the USB mass storage, right? And what is it going to boot your childhood photos? Well, it cannot. And for that reason, they had to implement some way for the BIOS to know, hey, does this mass storage device actually include any bootable code? And the way this is done depends on whether you're using a legacy BIOS or a UEFI BIOS. And I will talk about both, but first I'm going to be talking about the legacy BIOS. So we have the legacy BIOS. And it has a pretty simple system. Basically, what the legacy BIOS does is okay, I should probably first introduce the notion of a sector. So every mass storage device is split into equally sized chunks of data. Those chunks are called sectors. I will talk about the notion of a sector in more detail in the next lecture, but for now, just treat it as a 512 byte chunk of memory that mass storage devices are split into. And one important thing to know is that the first sector of a mass storage device is called its boot sector. That is because it typically contains information related to, well, as the name entails, boot. The booting process, right? So we have a boot sector, which is the first sector of your mass storage device. And what the legacy BIOS does is it loads your boot sector into the random access memory at the hexadecimal address 7C00. So it loads your boot sector into that address, and what it does is it tries to check the last word, a word being obviously 2 bytes, right? Basic computer science was a prerequisite. So it checks the last word, and this word is supposed to be this signature, right? So they implemented this mechanism that it's going to be a signature, and it's going to make sure that this is actually bootable. But they had to think of a signature, of course. It just had to be 16 bits of anything they desired. And they decided for the signature to have an extra function, that function being testing. To be precise, they decided that it would be a good test for the 8-bit buzz. And in order to do that, they did the following. They thought of the 8-bit value 01010101 10, and then the other value 10101010. Now, one very cool thing about these two values that you might notice is if you send them through an 8-bit bus, what these two values do is they flip every bit. So this 0 gets turned into a 1, this 1 gets turned into a 0, and so on. So this is a very good test of whether every bit can be flipped. So not only does it function as this boot signature that tells the BIOS, hey, this can actually be booted, CPU, please execute the stuff at the address 7C00. Not only does it function as this bootable signature, it also functions as a test for the 8-bit bus. Well, at least it did back in the day. This code is more commonly known in its hexadecimal form. If you convert this to hexadecimal, this is obviously a 5, this is obviously a 5, this is an A, and this is an A. This used to be actually a pretty common signature for not only booting, but many things. My IBM. Yeah, and not only IBM, right? So, 55AA, those have to be the 2 last bytes of your boot sector, and that is theoretically everything that is required in order for the legacy BIOS to boot something off of a mass storage device. One little quirk that I would like to mention is the x86 CPU is extremely little endian. It bases a lot of its functionality is based in little endian, and you should really remember that. And when it tries to read some value that it has, it will try to read it in little endian, and moreover, the reason this is important is because you have to remember when you read a singular value and then a singular value, you can't just get them together. You would have to reverse them to get the little endian version in comparison to if you read the whole thing, if it's supposed to be one value. Well, but it might have not been the best explanation. But what I mean is many assemblers adapt to this. And if you're going to be defining 2 separate bytes, then sure, you will define the byte hexadecimal 55 and AA, or you could just write down the whole thing in binary, or even convert it to decimal. I mean, it doesn't matter as long as your assembler supports it. But most assemblers, since they know how the x86 functions, and they know that it is very little endian in nature, you have to make sure that this is 0xAA55 when you're defining it as a single word. Because remember, when the x86 CPU will try to read these 2 bytes in this order, it will actually read it in reverse, obviously in reverse in comparison to big endian, because none is objectively correct. Or none of them is the universal base, right? But when it will try to read this value, it will read it the same as AA55. So you have to keep that in mind as a practical note. Yeah, so that's pretty much everything about the legacy BIOS booting process. Everything that it does is it goes through every mass storage device, and what it does is it loads its boot sector, so first 512 bytes mass storage device into the RAM address 7C00, and it checks if the last two values of that loaded in boot sector are 55 and then AA. If indeed those values are there, then it tells the CPU to start executing instructions at this RAM address, which in consequence is going to execute what we had in the boot sector initially. Yeah, and that's the whole process. Now, I'm going to talk about a couple practical remarks. So, you know, what you have to do pretty much in any assembly language, as you know, I've probably guessed, because, well, I've said it, is, you know, fill in some 510 bytes with anything that you want as a form of padding, and then just do a 55 and then AA. And you would define all of that as just data in assembly, and then assemble it to a binary format. So that is very simple. I would recommend for the value that you fill in the 510 bytes with to simply be a 0. That way your CPU is not going to misinterpret this as an instruction that it should not be doing. Or at least not the instruction we intended it to do. And for now we are intending for it to do nothing, but oh well. So you have to fill this in with zeros, and the thing is, you might say, okay, so I'm just going to do something like times 510 and then just like define byte 0, and then just I'm going to define a word which is going to be the hexadecimal AA55, and it's going to be fine. Well, yes, by itself it's going to be fine, but you're most likely going to be later placing code in your boot sector, and you can't just define it as a static 510. For that reason, it's better to adapt it. So we would have to subtract the amount of bytes that all of our previous instructions took up. So by default, that's obviously 0. But what is a consistent way to actually calculate it? Well, most assemblers allow you to get the current instruction number by just typing a $sign. So you would have a $sign, which would be the current instruction number, as in current instruction address, right? That's what I mean by that. And from that, you could simply subtract the hexadecimal 7C00. I mean, this obviously makes sense, because, let's say that you placed an instruction that took up 2 bytes, right? If you did that, well, since for 1 byte you have 1 corresponding memory address, right? Then the first instruction you would place would be loaded into RAM at 7C00. Then the second byte of the instruction would get loaded into 7C01. So obviously the next thing is going to be, the next address, the one that is going to be read by this, is going to be 7C02. And if you subtract 7C02 from 7C00, you're going to get 2. So it makes logical sense. You're going to subtract 2, and you're going to have 508, and cool, we will have 2 bytes of an instruction. We will have then 508 bytes of zeros, and then we will have 2 bytes of the signature. Cool, we fit in a single sector. Yeah, so this is one way to do it. However, some assemblers will not allow you to do this like that, and for that reason, you might want to replace this with a $sign, which is in many assemblers the symbol of the address of the section that you're in. Now we only have one quote-unquote section in all this code, so it's just going to interpret this as the very beginning, which is 7C00. If it does not interpret 7C00 as the beginning, then, well, you can set the origin in your assembly code as 0x7C00. Yeah, so that's the amount of times you would have to, that's the amount of bytes you have to fill with zeros. So how many bytes you have to define, and then assemble to a binary format. Grade school mathematics was theoretically not a prerequisite, but we are all competent people here, and we know that we can drop the parentheses and just replace this minus sign with a plus sign. And this is another way to represent this. If your assembler still does not accept this, then you might want to add the double $sign or 7C00 first, and then subtract the $sign. Because the reason it might not be working is because when you subtract the current address from 510, you're very likely to get, well, you're certain to get a negative number, and your assembler might not deal well with negative numbers. So you might want to do this first, adding this 7C00 and then subtracting the current address, because then you'll never have a negative value, unless the whole thing is a negative value, but this should never happen. Because remember, all of this just represents the amount of bytes that were taken up before this instruction, this part, right? So the only way for the whole thing to be negative is if you have filled up more than 510 bytes. And this should not be the case, because you should always remember, well, I only have one sector, the boot sector. This is the only sector I should actually place things in, and I have to remember I'm limited to 510 bytes because 2 bytes have to be reserved for the signature. Yeah. So that's basically how it works. And one other practical remark is that many biases, what we're going to do is we're going to interpret every OS as just code that is supposed to be executed, and it has an end. What I mean by that is you might have some executable code, and your BIOS will load that up and it will tell the CPU to execute that, and the CPU will execute that. But when the CPU has no more instructions to execute, the BIOS just says, okay, then I'm going to execute the next thing, which is the next mass storage device in your priority list. So this might have consequences. For example, let's say that you did all of that, you assembled it to a binary format, you flashed it onto a USB stick, and you plugged in your USB stick, you changed your BIOS configuration to boot from the USB stick first, and then your hard drive where you have your main OS. Cool, you plug in your USB stick, you turn your computer on, and instead of getting a black screen because, well, we didn't tell the code to anything, it boots your main OS. Why does that happen? Well, it can happen because if you didn't put any code, then when the CPU has no more instructions to do, the BIOS might just pick another mass storage device. And when that happens, it's going to go to your hard drive where you have your main OS and it's going to boot that. If you don't have anything on any of your devices, it's going to end up displaying no bootable device. And that's actually something that I have encountered that myself, where I once had a laptop that I was supposed to use for OS testing. This was like, I don't know, like 3-4 years ago. And I tried to boot my OS, and I saw this text. It was a pretty old laptop, and I saw this text, no bootable device. And I thought, well, perhaps something is wrong with the USB port or something, because I don't think it's a problem with my OS, right? So I was really wondering what's wrong. And it was just a very simple OS that didn't have anything at the end that would prevent it. Well, it didn't have an infinite loop, which I'm about to talk about. Basically, the problem was that it very quickly ended, and didn't. And because of the fact that it ended very quickly, the CPU didn't have anything to execute, and it tried to go to the overmass storage devices, detected that there's no OS in any of them, there's no bootable code because of the lack of a boot signature, and it just displayed no bootable devices. And I didn't even realize that it did boot my... Well, it wasn't really OS, it was just simple executable code that I was trying to test. So how do you prevent that? Well, you have to ensure that the CPU always has an instruction to do, and the easiest way to do that is with an infinite loop. And the easiest way to make an infinite loop on a low level is to use the jump instruction. So the x86 CPU, like pretty much any other architecture, has a jump instruction which simply jumps to an instruction in a given memory address. So you just do GMP in that's the mnemonic in most assemblers, and you simply do GMP and the current the memory address of the currently executed instruction, and see what this does, right? The address of the currently performed instruction is going to be the jump instruction. So it's going to jump to the jump to the jump. It's currently jumping to this memory address that tells us to jump to this memory address. So the CPU is in an infinite loop, and it will always have an instruction to execute. So it will never finish, and the BIOS will never try to load executable code of another MS storage device. So this is something worth adding at the beginning of your code. If you're too lazy to do the thing with the 510 and subtract that I did, I'm pretty sure that this only takes up 2 bytes. So you can just fill in 508 bytes with zeros and then do boot signature. Yeah, so that is basically it. If it comes to getting something basic to boot, right? So just you can do that. You can assemble all of that to a binary format. Then you simply flash it onto a USB stick or whatever mass store device you want to use. You go to your BIOS configuration, you change that, and congrats, you will probably have something that is a black screen, because that's what most BIOSes have by default. They're going to boot you into a black screen in what is called VGA text mode, 80 by 25 characters. That is the default in most BIOSes, but yeah. Not all of them, some of them will just print some basic entry message or whatever. It really depends on the specific model of your motherboard, or well, BIOS to be exact, in BIOS firmware. Yeah, so that's one way to do it, and as you can see, the only thing that is really fundamentally required is this boot signature at the end. And while this is the only requirement, people have figured out that, you know, there might be better ways to actually use this boot sector, not just immediately jump to other sectors that you load or whatever. Perhaps there is a better way to use this boot sector, and they created they created many standards for how you could use the boot sector, but none of them were as popular as the MBR. So there's the MBR, it stands for Master Boot Record, and it's a very popular standard of how you should use your boot sector. And I just like to say, this is all, you know, human abstraction, and it's not a hardware requirement. So the idea of the MBR is you have your boot sector, and you get a huge chunk, way larger than this. This is not a proper scale, but I just want to fit all of the other stuff. But you get to execute any code you want. This will probably be some initialization code, loading more disk space, stuff like that. For all of that, you get 440 bytes. Yeah, so you get a pretty big amount of bytes for code. Then the next thing you have to put right after your code is a disk signature. You have to put a disk signature, which is going to uniquely identify the disk you're putting on, where disk is just a very general term for any mass storage device. This signature is 4 bytes. And then, as a form of padding, as a form of filling this to 512 bytes, which they decided to put right after the disk signature, you have a reserved section, which is supposed to just be zeros, and to be precise, it's 2 bytes of zeros. After that, you have what is called a partition table, right? So you probably know that a partition is a sort of given section of the disk, which has a determined starting and ending point. It's a way to split up the disk in some smaller sections, right? Which might have a dedicated function, might not. But yeah, so you have your partition table, and there's a fixed size of partitions, which even in a modern UEFI system, many OSs still decide to have a limit of 4 partitions as this sort of consequence of the earlier MBR. But the MBR allows you for 4 partitions. So you have 4 partition descriptors that are going to describe your partitions. So you're going to have your first partition, your second partition, your third partition, and then fourth partition. I started to write that in a different format. Partition 4. And if it comes to the partition table, which is going to describe your partitions, this is also something called the proper partition table. It is going to have 4 entries of 16 bytes. So you have 4 entries, 1 for each partition, and 1 entry is 16 bytes. And then the last 2 bytes are your AA55 signature, as it is a hardware requirement. Yeah, so this is the entire structure of the MBR. You get 440 bytes for code, 4 bytes for the disk signature, 2 bytes of just zeros, 4 16-byte partition entries, and then the the boot signature. Yeah, so this is the MBR. As I said, this is not a requirement, and let's be honest here, the only time you would actually need to implement an MBR is when you're actually developing a file system. Now, some OSDevs decide to implement a file system very early on, and sure, you could do that, and I'm not discouraging you to do that. I just want to say that the MBR is something you only need if you are going to implement a file system. Because then when you actually read data off of the disks and stuff, then this is when you will need a disk signature and a partition table, right? And this is just a very popular standard, and standards are good to follow. Many people nowadays, they try to create innovative stuff, and I'm not saying I'm against that, but many of them actually regret that they didn't follow standards from the start. Because many people, for example, say, no, I'm not going to boot from like ELF files, I'm going to create my own executable format. And cool, I mean, I guess you can then like say, I made an OS with my own executable format, and that's cool, and I'm not discouraging it. But many people then, I'm just saying, many people then later regret it because they realize, well, now I have to make my own compiler for all of that and stuff, and I don't have compatibility with like ELF stuff. And I just want to say that as a rule of thumb, it's good to follow standards. Yeah, I just wanted to point that out. So, sure, follow the MBR, but what I'm saying is you don't have to do it very early on, because when you will be actually reading data from the disk, then and actually trying to read like more complicated data and a whole file system up of that, then sure, this may prove useful, but I mean, it's not necessary at the very beginning if you don't want a file system early on. So yeah, you can easily read about those partition standards, how those 16 bytes of data are actually used, and you can go ahead and implement that. I'm not going to cover that. Perhaps I'm going to cover the MBR in more detail when I'll be actually talking about implementing a file system, which I actually plan on doing pretty late in this series. Yeah, that's it. So the MBR is the standard that you can follow in order to then, you know, read data of partitions and have your disk split into partitions. This is, as I said, following standards is good, because then when you will be at a point where you have to port software and the software is going to try to create partitions and it's going to use those 16-byte descriptors used by the MBR, then you'll already have an implementation of that. And yeah. So, I think I talked about the legacy bias pretty extensively. So, now's the time for the UEFI. So, the UEFI has a completely different way of checking whether something is even bootable and then booting. It does it by checking for something called a valid GPT or GUID partition table. So I'm just going to draw one big disk, one big mass storage device. Let's say something like that. And the first thing that it checks for is there a valid GPT, which in reality is quite small, but you know, I'll have to draw a lot of things here, which is why I'm going to make it graphically big again, not up to scale. So this is the GPT, or the GUID partition table. If you don't know what a GUID is, it stands for Globally Unique Identifier. It's a pretty long hexadecimal string. I think it has 128 hexadecimal digits, if I recall correctly. So you have a lot of combinations. And the idea is that you have to be extremely, in fact, like universally incomprehensibly unlucky in order to get the same, in order to generate the same GUID as someone else. Which is why it's used to globally, uniquely identify something, a globally unique identifier, the GUID. So we have a GUID partition table. It's called that because it is going to, every partition table in UEFI needs to be unique. Excuse me. It needs to be unique. And to determine this uniqueness, a GUID is used. I highly apologize for sneezing there. Now, the first sector of the mass storage device doesn't really change. It's still something called the protective MBR. I'm just going to write MBR down. So this is the protective MBR. And this is why I wanted to introduce the notion of the MBR, so that I can actually talk about it being in the GPT. So we have this protective master boot record. The idea is that obviously when UEFI was a new thing and people started selling operating systems that were supposed to be run on motherboards that support UEFI, you know, some of those people would, you know, not be so tech savvy or not even just look into their BIOS or whatever, and they would not know that their motherboard does not indeed support UEFI, or they do not know how to turn on UEFI in their BIOS configuration. For that reason, they added a protective MBR, and as the name suggests, it's a form of protection, because it just makes sure that if it's booted on a legacy device, it can still attempt to even boot. This could be the whole OS. This is a very rare thing, but for like very solid, very popular OSs, this is a thing where the MBR actually just boots the whole OS. But this is still relatively rare, and what will usually happen is the MBR is there to boot some code which tells you that you should run this on UEFI. Or the MBR might boot the whole OS, but it will first boot a little warning that says, hey, you should really be running this on UEFI. So this is the protective MBR. Then over here and over here, you have GPT headers, which simply describe some information about the GUID partition table. This one is called the primary GPT header, whereas this one is called the secondary GPT header. So you have the primary and the secondary GPT headers, and over here you'll have some entries. And then in the middle you'll have your actual proper partition table. So this is your proper partition table, which actually describes all of the partitions. So the GPT is a bit more of a complicated structure, as you can see. It's a bit more sophisticated, and the UEFI checks if the GPT is even valid, and if it is, then it's going to try to boot the mass storage device, and well, it will not boot it if it's not a valid GPT. This is even more secure than what would be the signature system on the legacy BIOS, and the reason for that is, well, if you just have data written on a mass storage device and it's not supposed to be code, there is still an extremely slim chance that it will have the signature in place. It's highly unlikely, but it could happen. And then it's just going to interpret your data as some gibberish code. But there's an even slimmer chance, basically impossible, that there is a whole valid GPT on the mass storage device, and this wasn't someone's intention. Okay, so we have this GPT, right? And one thing that a UEFI booting system requires is it doesn't care about other partitions, but there needs to be at least one partition formatted with the file allocation table 32 file system, or the FAT32. So this is a pretty common file system. You've probably encountered it in your daily usage previously. So it needs a FAT32 so-called boot partition. So you have a FAT32 boot partition, which obviously the partition table points to. And it's an extremely important partition because it's going to contain a directory called EFI/boot. And this is a very important directory because this directory actually includes all of the... So the thing is, operating systems in UEFI are actually just executable files. And they're in a format called PE, or portable executable. This isn't really like a wild format or anything. Portable executable is the format that .exe files use on Windows, and also .dll files, right? So Windows dynamic libraries also use the portable executable format. And operating systems, or at least their initial code, is just a PE executable. And all those PE executables of the different OSs you might have on a mass storage device have to be placed in the FAT32 boot partition in the EFI boot directory. And the placement of the partition and everything will be specified by the GPT, right? So there are custom, let's say EFI, okay, so it's going to contain a PE executable, but this PE executable is not going to have a .exe or .dll extension. It is going to be a .efi file. And there are custom names designed for some special purposes. For example, obviously Windows, being such a popular operating system, has its own windows.efi file. But by default, what it is going to try to boot is a file which is called boot, then the name of your architecture. If you're using x86_64, that just counts as x64, by the way. And then .efi, right? So since I said that this is going to be focusing, well, I'm not going to be presenting much stuff with the UEFI, so it doesn't really matter, but since I said that this is going to be focused on an x86 OS, and I will present how to go into long mode, which is a 64-bit mode. So I will assume that one is using x64, right? So you would place a PE file, which would have the path EFI boot, then boot. I hit my mic, I'm sorry. I think I'm going to just actually shift it to the left a little bit so that it actually fits. So over here, EFI boot / boot x64.EFI. So, right, it's .EFI, but it's not some wild executable format. It's just the standard PE, which most people are familiar with, at least familiar with the existence of exe and DLL files. And yeah, that's how a UEFI system boots. And as I said, most people use tools for all of those things. Just like you can just define data in assembly, and this is usually how people make an MBR, or even just a boot sector that does not follow the MBR standard. They make it in like assembly, it's just defining data. A very small amount of people make their GPT entirely manually, and they usually just use a tool in their OS user space that is going to generate GPT for them. I'm not saying that's everyone, and I'm also not saying that if they do that, it's a bad thing, but that's just what most people do. And right, this GPT is going to tell where the FAT32 boot partition is, and this boot partition will have the EFI boot architecture.EFI file. And again, this has to be a portable executable. And for that, it would really, you could also just do it in assembly, but the thing is, you would just have over 200 lines of just headers, just filling a bunch of ones and zeros through defined bytes that corresponds to different flags in the header. So yeah. And then you'd, to communicate with the UEFI, to perform those input-output stuff that it allows you to do, you'd have to contact boot services, which also is pretty difficult to do without an external library. Yeah. So it's way more difficult to actually practically do. I mean, I have tried doing all of that in assembly, and I have managed to do that once, and I don't think I ever want to do it again. And let me tell you, just the PE file, it was literally hours upon hours of just filling in headers, and it wasn't that fun. Yeah, I think the thing is, the headers in the PE file, like, I don't understand Microsoft. The headers are just so stupid. You give the file, you give the header some information, and you define a whole byte for it, and then you have another point in the header, and it has the exact same information that you have to give to it, but it can't just copy it because the information is in a different order. So you'd have to change the bits manually. And I don't know who invented the PE headers, but they are horrible. I mean, I personally dislike them. I have no idea if there was some good motivation for doing that stuff, if there were rational reasons behind that, but yeah. That's how booting in UEFI works. I just wanted to present that, so there is this perspective of not only how the legacy BIOS booted, and I think that is everything I wanted to say. So now you know how we can even get some code on a mass that is on a mass storage device, and you obviously get it on a mass storage device by having a binary file, just flashing it with a program like, I have no idea how it's pronounced, Balena Etcher. It's B-A-L-E-N-A. It's the one I recommend. You just flash it onto a mass storage device and it's there, and you boot it, you mess with your BIOS configuration. Many BIOSes even have a key that you can press so that a list shows up and you can pick the device you want to boot from. Some BIOSes allow you to, by default, just show you this list, and you can, each time you boot your computer, select the device you're booting from. But yeah, we know how to, from a mass storage device, you know, how to even make some code that one can assemble into a binary format, flash it, and then we understand how this booting works. And congratulations if you've understood all of this and you can write assembly code, then you should, with a bit of tinkering, perhaps help from some forum if you're stuck, but this shouldn't be the case. Write an OS that boots. This is, in the legacy BIOS, that's just pretty much 3 lines of code, but I wanted to cover it in fine detail, and I will try to cover everything in this series in fine detail. This is my philosophy. I want people to really understand operating system development. Yeah. I think that's actually everything I wanted to say, and thank you very much for watching, and I hope you'll see the next video where I'll be talking about using the BIOS to our advantage and having it perform input-output operations. Thank you very much for watching this video.